So in this video, I want to give some of the details of an example that we discussed in class. So in this example, our metric space was R2, the plane, with the Euclidean metric as usual. And our set E was the Cartesian product of the interval -1, 2, half closed, there it is here, with the open interval 1, 3. So there it is here. So if you were to draw this set here in the plane, you would get this region that you see right here. All right, well, what we wanted to do was show that the interior of this set was, well, intuitively we think of the interior of a set as the set itself without any points that happen to lie on the boundary of E. So what we want to do is we want to remove this line, or so we think, in order to get the interior of E. If we do that, we'll end up with this set here, which can be described as the Cartesian product of the open interval 1, 2, there it is, with the open interval 1, 3. There it is here. Alright, so that's what we wanted to show. And what did we decide? Well, if we're going to show that this set here is the interior of E, what do we need to do? Well, we need to pick a point X, first of all, that lies in this set 1, 2 cross 1, 3. So let's take such a point. So I'm going to draw it in here. Let's say it looks like, I don't know, maybe it looks like that. Alright, so here is our X, and it has a first coordinate, call it x1, and it has a second coordinate, over here we'll call it x2. And looking at this, it looks like if we took epsilon to be the shortest distance between x and this point here, this point here, this point here, and this point here, we would end up with an epsilon neighborhood about x that, so we took this to be our epsilon, we took that to be our epsilon. It seems that the epsilon neighborhood about that x should lie entirely inside of E. So what was that epsilon that we said? Well, it was supposed to be the shortest distance between this point and this point, which you'll notice is the distance between x1 and 2. This point and this point, which is the distance from x1 and 1. This point and this point, which is the distance from x2 to 1, and this point and this point, which was the distance from x2 to 3. So in other words, we wanted to take our epsilon here to be equal to the minimum distance, the minimum of these distances that we see here. And because x1 is supposed to be between 1 and 2, strictly between 1 and 2, and because x2 is supposed to be strictly between 1 and 3, there it is, and there it is here, it should be clear that each of these distances here is bigger than 0, and therefore the minimum of these four distances will also be bigger than 0. Alright, so what do we want to do? We want to show that this epsilon is going to work. So in other words, we want to show that the epsilon neighborhood about x, with epsilon as chosen here, is contained in, we'll show that it's actually contained in open 1, 2 cross 1, 3, and that, of course, is contained in our set E. So how are we going to show this? This is what we need to show in order to show that x is in the interior of E, right? Given our x, we needed to find an epsilon greater than 0 such that the epsilon neighborhood about x is contained in E to show that x is in the interior. So if we have in fact shown this, we'll have shown that x is in the interior. Okay, so this is what we're trying to show right now. So to see this, what are we going to do? Well, What we could do is pick a y in here and show that it lies in here. Instead, what we're going to do is the contrapositive of that. We're going to pick a y that's not in here and show that that y cannot belong to here. So to see this, we're going to pick a y. It's going to have two coordinates, a y1 and a y2, which isn't in this set here. So it isn't in 1, 2 crossed 1, 3, and we want to show that y is not in the epsilon neighborhood about x. If we've done that, we'll have shown this. Okay, so how are we going to do that? Well, because our y isn't in this interval here, either y1 is not in the interval 1, 2, or y2 is not in the interval 1, 3. Let's write that down. So we can say either y1 is not in 1, 2, or y2 is not in 1, 3. All right, so let's suppose first that y1 is not in the open interval 1, 2. Well, then either y1 is going to be bigger than 2, or y1 is less than 1. So, what can we say? Either, what are our situations? Either what's true? Well, let's just draw a little picture here. Either we're in this situation here, where we have our open interval 1, 2. Here is x1 that we know sits between 1 and 2. And maybe we have this situation where y1 is bigger than 2, or maybe we have this situation here. Here's 1, here's 2. Just drawing it over to the side a bit here. Here's our x1, and maybe we said y1 is less than 1, in which case y1 is sitting over here. So either, what do we have? Either y1 is, either y1 is bigger than 2, and if y1 is bigger than 2, then notice that the distance from y1 to x1 is going to be bigger than the distance from x1 to 2. So either we are going to have that the distance from x1 to 2 is less than or equal to the distance from x1 to y1, or we're going to have that we're in this situation over here, in which case notice that the distance from x1 to y1 is greater than or equal to the distance from x1 to 1. So, or right here, the distance from x1 to 1 is less than or equal to the distance from x1 to y1. But recall that our epsilon that we chose was the minimum of 4 distances, of which this was one of the distances, and of which this was one of the distances. So I know that this number here is at least as big as epsilon, and this number here is at least as big as epsilon. Okay, so what do we know? We know that in the case that y1 is not in 1, 2, either this distance is bigger than epsilon or this distance is bigger than epsilon, and therefore, what can we say? In either case, we get that the distance from x1 to y1 is greater than or equal to epsilon, and we can also say looking up here. So let's come back up here. What did we show? We showed that if y1 wasn't in 1, 2, this distance is greater than or equal to epsilon. And similarly, if our y2 isn't in 1, 3, we can say that the distance from x2 to y2 is greater than or equal to epsilon. All right, so let's just write that down. Similarly, if y2 is not in 1, 3, we can say that the distance from x2 to y2 is greater than or equal to epsilon. All right, so what have we shown? Well, we have shown that if y is not in this interval, then either this is true or this is true. So one of these two terms is going to be greater than or equal to epsilon, and therefore we can say that if we take this term here and square it, and this term here and square it, well, either this term squared is greater than or equal to this term squared, so either this term is greater than or equal to epsilon squared, or this term squared is greater than or equal to epsilon squared, and both are greater than or equal to 0, so the sum is certainly going to be greater than or equal to epsilon squared plus 0, if you like, which is epsilon squared. Well, that means that if I put some square roots over top, the inequality is going to be maintained. So we know that square roots preserve order. And what's this? Well, let's just notice that on the left here, we don't need these absolute values here. If we're going to square the terms, so you could write x1 minus y1 squared plus x2 minus y2 squared, and you'll notice that this is the formula for the Euclidean distance between the point x1, x2 and y1, y2. In other words, the formula for the distance between x and y. In other words, this is true. The distance from x to y is greater than or equal to epsilon, and that means that y is not in the epsilon neighborhood about x as needed. Alright, so what have we shown? We've shown as we said before, that the epsilon neighborhood about our x as chosen is indeed in 1, 2 cross 1, 3, which is contained in E. Okay, so what have we shown? We've shown that if we pick any x in this set here, x is in the interior of E. Right? So in other words, we've shown that one, 2 cross 1, 3 is contained in the interior of E. And now, finally, to show that the interior of E is exactly equal to this set, we'll show that any point that is in E, but not in this set, is not in the interior. Alright, so what do we do now? So now suppose that that we have a point x equal to x1, x2 that lies in E, but is not in this set here. Well, what does that mean? Well, that means that if you look way back up here at our picture, if we have a point that's in E, but it's not in this set here, then in fact we have a point that's somewhere along this line here. So let's go down and draw a picture of our point in this set. So what do we have? Well, x, so let's just write that is, x looks like, well, its first coordinate is necessarily 2, and its second coordinate is x2. And what do we want to do? We want to show, look a little more square, we want to show that x is not in the interior of E, so what do we do? Well, we need to show that there is no epsilon neighborhood about this x which is contained entirely in E. So we are going to take an epsilon greater than 0, and we want to show that the epsilon neighborhood about this x is not contained in E. And how do we do that? Well, we let epsilon greater than 0, and we note that the point, well, let's take this point right here, which is going to look like 2 plus epsilon over 2. So we just moved a little bit to the right here. We took 2 plus epsilon over 2 for our first coordinate, and we'll use exactly the same second coordinate. So, comma, x2. Note that y equal to 2 plus epsilon over 2, x2 is in the epsilon neighborhood about x, y, because the distance between our x and y is equal to epsilon over 2. I'll let you check that. Just using the formula for the Euclidean norm. So what do you do? It's 2 plus epsilon over 2 minus 2 all squared is epsilon over 2 squared, plus x2 minus x2 all squared is 0. So we have epsilon over 2 squared. We take the square root of that, and we end up with epsilon over 2. So you can check that. So, as we said, y is in the epsilon neighborhood about x, but because the first coordinate of y is greater than 2, we know that y doesn't belong to E. So, but y is not in E. So, what we said, therefore, this epsilon neighborhood about our point x is not contained in E, and this epsilon greater than 0 was arbitrary, so no epsilon neighborhood about x when x lies along this line here is going to be contained in E. No x along this line here then is in the interior of E. So this completes the proof. So this completes our proof that E is equal to the open interval, E interior is equal to the open interval 1, 2 crossed with 1, 3. And we are done.